Hello and welcome to my video for Lab 3 or the Black Hole Lab. Alright, so there are two parts of this lab. For the first part, we are constructing a computational model to simulate a star's trajectory when influenced by the gravitational force of a black hole. And then we're using this model to estimate the mass of the black hole. And then using this mass in the second part of the experiment, which asks us to construct another model to determine the initial speed necessary for a spaceship to break orbit of both the black hole and the planet orbiting the black hole. Looks like a hat, but it's a spaceship, I swear. And then an overview. This is the mass that we wound up finding and the escape speed. So the main equation that was used in both parts of this experiment was Newton's second law, which basically says that the net force in the equation is equal, the net force in an experiment is equal to the change in momentum over change in time. And then because this is equal, we are able to separate the net force into parallel and perpendicular components, which allows us to sum them together, which is the main part of part 1 of this experiment. So the other part of this experiment is the gravitational force. So this experiment occurs in space. The system in part 1 is the star, and the only other thing in the surroundings is the black hole in space. Since space is a vacuum, it does no work on the star, and so the only force acting in part 1 of the experiment is the gravitational force on the star by the hole. And so Fnet, or Fg, is equal to this equation, and then the variables are defined on here. So in part 2, the system is the spaceship and the surroundings are space, the black hole, and the planet that it is leaving. Since space is still a vacuum, the net force is equal to the sum of the gravitational forces of both the black hole and the planet. So this experiment is fully computational. The short answer is that you cannot go near a black hole. But the long answer is that a computational model will let us simulate these conditions in experiments that would be otherwise physically impossible to carry out. And it also allows us to isolate those forces and energies that we want to analyze and observe. So in part 1, initially, a star is orbiting a black hole of unknown mass located at the origin, and the mass of the star is given as this value. The radius was given by the personal key we used with our little emails. So the first part of my code is basically equating the net force to the change in momentum over change in time, and then because of that I'm able to separate the net force into perpendicular and parallel components right down here. And then through some manipulation of the Fnet or Fg equation, I was able to isolate the unknown mass of the black hole in long. Here's like a longer version of all that. And then the mass of the black hole is determined to be around this number with some rounding. So for part 2, a spaceship is taking off from a planet that is orbiting a black hole located at the origin. Here are the initial masses and then the initial positions, as well as the position of the black hole, which was fixed. So in this computational model, we determined the initial speed through just trial and error. Down here, as we said earlier, the net force is equal to the sum of gravitational forces. So you can see down here the net force equal to the sum of both of these forces. And then in order to model the trajectory of the planet and the ship, we use the position and velocity update formulas, which are determined a bit better here. And so then the initial velocity found the trial and error was determined to be this value in meters over seconds. Because this lab was fully computational, no experimental data was collected. However, we can still compare we can still analyze or discuss a little bit of sources of error. So some systematic error that could have occurred in this equation were some rounding errors in the calculation. So this entire experiment was coded in Python, which has like a limit to how many numbers it can round to, which could have affected a number of the variables used, especially when we were calculating the mass of the black hole. And then some random error could have occurred in the human error and input of numbers or calculations. So for part 1, what does it mean? As outlined in Newton's second law, the net force is equal to change in momentum with respect to time. And since this relationship is proven true, we're able to conclude that its components are that its components are identical as well, which allows us to equate the perpendicular and parallel components of both Fnet and dp over dt. And then for part 2, what if we wanted to orbit the black hole? If we wanted to do that, we would need something called the orbital speed, which is the term that's used to describe the speed at which an object maintains orbit around a body. and it's a special speed that can never be exceeded or like can't go less than it either, which means that whatever initial speed we find, it has to be one that, when affected by the force of gravity from the black hole and planet, will still not change. Thank you for watching my video. And yeah, have a great day.